Let's put this down. Okay, it's Earth Science time. We're going to talk about groundwater. Let's get that out of the way too. Groundwater storage. Your book calls it groundwater storage and movement, and we will talk about the movement as well, but to me this is a briefer and more accurate title. So the first thing your book mentions, and we've talked about this before, is the hydrosphere. You know what the hydrosphere is, right? What's the hydrosphere? Is it a specific place on planet Earth?
It's in the air.
Yeah, it's everywhere. Right, it's everywhere, is that what you said?
Anything on planet Earth.
Yeah, it's all the water on planet Earth, right? When we think about all the water on planet Earth together, that's called the hydrosphere. And that's, you are aware that the word, or the root of a word hydros means relating to water, right? So like if you were to remain hydrated in the basketball game, that's because you need to drink lots of water, right? If you get dehydrated, it's because you haven't got enough water. So hydros means water, and then sphere is, you know, it really means the shape sphere, but in this case it's talking about all the water on planet Earth. So look at this little chart with me. Where is most of the water on planet Earth located? And this is you probably won't even need to look at the chart for this. Where is it? The oceans. The oceans. After that, the ice caps. It includes glaciers in that amount. And then third, and this is what's important for us right now, groundwater. So more than all the water in lakes and all the water in the atmosphere and all the water in rivers and streams is groundwater. So apart from the oceans and the ice caps and glaciers, the groundwater is where most of the water on Earth is stored, right? We talked about already the process. I'm just going to remind you of these. Runoff, infiltration, and evaporation, right? And the one of those that's going to apply here is infiltration. And let's redefine this just because we were talking about that mostly today. What's infiltration?
Is it water soaks into the ground?
Yeah, water soaks into the ground itself. Let's be more specific now that we can. Water soaks into precipitation from the sky will soak into the pore spaces between what, generally? Pore spaces between sediment. Right? Did you find in your lab that there was a linear relationship with grain size and porosity? Like, did the one with the highest grain size necessarily have the highest porosity? No, like if you look at your data, that's obviously not the case. There's a lot of other factors. Really, we'll find here in a second, or well, you can just look at this picture and find out for yourself. But more than grain size itself, the thing that affects porosity the most is sorting. Sorting affects porosity. And when we say this word porosity, let's just define that real quick. Porosity is the relationship between what two things? Oops, let me switch this over. What's porosity the relationship between? That's not really a good way to phrase a sentence, but you know what I mean. Between what and what?
Water and pore size.
Yeah, relationship between pore spaces, right? The volume of the pore spaces versus what? Divided by what? What did we divide it by in your lab?
How much water?
No, that was the volume of the pore spaces was how much water it could fit, divided by the volume of the sediment versus volume of sediment. Can it ever be greater than 100? No, right? Because we're dividing by the total volume of that chunk of sediment, right? If we have a 100 milliliter chunk of sediment, we can't fit 110 milliliters of water in it. It wouldn't work, right? I mean, well, we could pour 110 milliliters of water in, but some of it would have to come out. Do you see what I mean? In a certain volume of sediment, we can never have more than that volume of pore space. And we express this as a percentage, right? Which is a fairly easy way to do it. So, looking at this little chart of sorting, which of those little three pictures there, we have well-sorted large sand grains, unsorted sand grains, and well-sorted small sand grains. You might have, if the linear relationship were true, we would expect the well-sorted small grains to have the lowest porosity. Is that what you find in this picture? Just looking at it, right? We could actually calculate, but is it true that that has the lowest, or sorry, the lowest porosity? Which one of those does have the lowest porosity?
Unsorted grain.
Yeah, those three pictures on the bottom of the page, we're looking at which of them has the lowest porosity, and the unsorted one has the lowest porosity, because what could have been filled in with water is instead filled in with smaller little sediments, right? So basically the pictures look like this. We got big daddy grains with other size grains in between, and then only small grains. Right, and like I said, we almost, before we looked at these pictures, we might expect, like if someone just said which would have the largest porosity from our lab, we'd expect this one to be the most. But what happens is this one, the little gaps get filled in with smaller sediment. So this one has the lowest porosity. And this is important because when we move on, I'm just going to erase it because you have the picture in your book, which is better anyway. But this is important because what happens is the ground itself, made of sediment, usually in places where the bedrock is sedimentary, like here, the ground itself can absorb water, right? As water falls down, some of it runs off, some of it evaporates, but a large amount of it infiltrates it. It soaks into the ground. Yes, Maddie?
Okay, so I know this is like seem like a really good question because I'm trying to think about how to say it. Okay, so you have rocks, and when me and Skylar poured the water into the tube, there was like this much water, but it looked like it was so high because of how heavy it was. How does it like even itself out like that?
You mean like how does it form a flat level? Is that what you mean?
Well, like we didn't pour that much in there, but it would still look like a lot. And then I know it was because the rocks are heavier, but how does it make it like spread it out so?
Oh, so like it goes all the way to the bottom, is that what you mean? Like so it soaks through? So that's what we're going to talk about in a second, because there's a difference between this porosity and this other word that we're going to, are you guys all done with the porosity? What Maddie is talking about is something else separate called permeability. So something can be porous but not permeable. And you remember maybe the word permeability from biology too, but basically in places where the bedrock is sedimentary like this, the ground is often also permeable. We call it permeability. Let's spell it right though. Permeability is the property where not only porosity we could have defined as, remember we just said the relationship between the pore spaces in a rock and the rock itself, right? But permeability is the ability of water or other fluids, right? Because what other things can be stored in the pore spaces of rock besides water?
Mud.
Mud, maybe. What else?
Like roots.
Maybe, yeah. I'm thinking of other liquids. What other liquids can we commonly find underground?
Magma.
Probably not magma, because it would melt the rock usually. I don't know, maybe sometimes. What?
Gas.
Yeah, like natural gas, which is actually a gas, but also petroleum products, basically like oil, right? But it's the ability of water or other fluids, the ability of water or other fluids to go through a layer of sediment or rock. So we could think of a time when a rock might be porous but not permeable. Do you see the difference? Because permeable means that it can go all the way through. When might something be porous but not permeable?
Go through a layer of sediment.
Yeah, or a rock. So porous means that it can hold water in its pore spaces.
So
Well, yeah, what?
With our rocks, like our large pebbles that we use, they didn't like soak up any water at all.
So the pebbles themselves, you're saying, did not have, the water couldn't go through them, right? It could fit in between the cracks.
Yes, but
Yeah,
it
so
couldn't go
so one of those, probably a single one of those pebbles, probably not permeable, right? But when they're all together, they have pore spaces. I was thinking of something like pumice, where you know about pumice, right? So pumice is, we talked about it, it's an igneous rock. You should know about pumice. I'm going to draw a little block of pumice here. It's got all these little holes in it, right?
Sometimes you use it to clean stuff.
Sometimes you use it to clean off your scabby little feet. But if you were to pour water on this, maybe the water would get in these first few, but because the holes are not connected, it can't go from this hole to this hole because the in-between is impermeable, right? So this has pore spaces. A certain amount of it can be full of fluids, but they aren't connected, and so it's not permeable. Does that make sense? So there's a difference between permeability and porosity. But generally, if a rock is porous, it's also permeable. Generally. That's not always true, but it's generally true. So when the rain falls on the landscape, here's the landscape. Here's the rain. I got blue right here. Some of it runs off, right? Probably not here because I tried to draw this pretty flat. Some of it evaporates, but some of it also infiltrates. And so if the rock is permeable enough, the water eventually goes right through or right into that layer of rock, right? And so a common misconception is that when we talk about this word aquifer, or at least to me it was a misconception when I was a kid, maybe because I played Mario, but in one of the levels of Mario you go and there's an underground lake. Oh neat, a cave and there's a lake. Oh wow, so cool. I thought that's what an aquifer was. So when my second grade teacher said the world's largest aquifer is here underneath our feet, I was like, well, I better not jump too hard or I'm going to fall through and land 4 miles down in a lake and drown, right? And so this is the kind of thing I'm worried about all the time. This is why I'm a broken person. But it's not the truth. That's not how aquifers work at all. They don't. It's not a big old hole underground with a lake in it, usually. That does sometimes happen. We'll talk about that in maybe either the next lesson or the one after that. But generally, it's just a layer of rock that has enough permeability and porosity that can hold water in it. So the rock, it acts more like a sponge, right? It's a thing, a physical substance, right? But it can have water within it. So the water will eventually soak down, and it'll reach this base level. There's still, all this is rock. What kind of rock am I drawing here or trying to draw here? What do these dots represent? No.
Is it well sorted?
Well, it's what? What did you say? Well sorted what?
Small.
Yeah, what do the dots represent? What size sediment do we represent with dots? Sand. So what kind of rock is this?
That's why I said sand.
Yeah, okay. It's sandstone. Right, so this sandstone is both permeable and porous. And so the water, as it filters down through these pore spaces, flattens out. Just like if I were to dump my tea, right, or if you spilled some water, that would flatten itself out. It does the same exact thing underground, right? And it forms this layer of water, and this layer is called the water table. So the water table is this line. Are you writing any of this down? The water table is this line where above the water table, what are the pore spaces full of?
Water.
No,
Air.
above they're full of air.
Yeah.
And this is called the zone of aeration. So above the water table is the zone of aeration where all the pore spaces are full of air, or most of them are full of air. And below it, can you guess?
Zone of saturation.
Zone of saturation. Below it, they're saturated with water. So every pore space in this sandstone below the water table is saturated with water. And the rock itself is called an aquifer. We talked about this a couple lessons back too. The rock itself is called an aquifer. There's no special name for the water held within it, it's just water. But this rock is called an aquifer. Aquifer means aqua. What's that mean? Aqua. Water, right? It's Latin. Hydro is Greek for water. Aqua is Latin for water. And then this fer, the suffix fer means it holds it. It can carry it. Christopher. You know Christopher? That name means someone who carries Christ. Aquifer is a rock that carries water. Anyway, so the aquifer, this layer of rock, has water within it, soaked in. Okay?
I was thinking the same.
Water table, zone of aeration, zone of saturation. The water also, you should be aware, the water under here, the water in this rock flows just maybe not just like water on the surface, but it does. It'll flow downhill like water does. So if this,
So does it down cut, or is that not?
I'm sorry, what?
Is it like down cut still?
Oh, like the river?
Yeah.
Generally not. So this is the water.
Because it's all on a base.
Yeah, there is some erosion probably occurring, but it isn't flowing like a rushing river. Like for instance, what I mean is that imagine this is a much larger landscape. Pretend this is like hundreds of miles, okay? And it rains. Okay, it rains here, but not here. What's going to happen is this water table will build up water because the water does flow more slowly since it's got to go through all the little cracks. Like you noticed that yesterday. When you poured the water in, it didn't go splash right to the bottom like it would if the beaker were empty, right? It took a while to infiltrate. So everything happens a little bit slower in the aquifer than it would on the surface. So water builds up here where there was the most rain, and slowly, over time, it will level out at a higher level than it was before. Does that kind of make sense? So it will flow in that way, but because it's such a slow process, I don't think really there's not down cutting certainly associated with it. And to the extent that there's erosion at all, it's only very minimal. Does that make sense? So the water kind of bubbles up where it's raining, and then it slowly evens out. That's why the water table can be higher in one area than another, right? Especially if it just rained. And the water table can lower and raise over time depending on how much rain the environment is getting. So then what is preventing all of this water from just soaking down into the planet core? What's stopping it here?
Is it that layer of bedrock, rock and stuff?
Yeah, so this is the bedrock, but there might be another layer of rock under it that is what? How would we describe it? What? Let's say it's not permeable, it's impermeable, right? Because permeable means it can flow through. So this is going to be impermeable rock, which we call an aquiclude. Aquiclude. This is aqua still meaning water, and clude, to occlude something is to make it shadowed, right? It's not I think it's a cool word, but it doesn't exactly mean, you can think of it this way, it excludes water from it, right? What kind of rocks do you think would make a good aquiclude? What kind of rocks would be impermeable? As an example. Can you think of any other kinds of rock besides sandstone? What about granite? Do you think granite would be permeable or impermeable?
Rock.
Yeah, granite is rock. Granite would be impermeable. Yeah, clay. So if we have something like shale, which is made of clay, probably impermeable. In fact, the most common is shale, which we represent like this. An aquiclude made of shale. Well, maybe not all, but almost all metamorphic and igneous rocks are impermeable just because of the way they were made, right? In both of those processes, the crystals grow together in igneous rocks, which would exclude water, and in metamorphic rocks, they're packed together so tightly that they would probably exclude water. So any igneous or metamorphic rock, shale, limestone, it depends. We're going to talk more about limestone in the next lesson. But pretend now, well, let's do this last thing. Pretend, so over the distance, this layer of rock, there's like a hill here. You're aware that hills exist. Right here where this water table is going to be, the water can flow out from here. And this little area here, can you see this at all on the, yeah, you can see that pretty good. This is called a spring. This is this is probably the main way the springs form. When just the water table is above a hillside, right, there's a spring there. On page 257, there's a go to 257, there's a little chart of different kinds of springs. But anytime that the groundwater is becoming surface water, we call that a spring. When you think of a spring, you might think of like water jetting out of the ground. That's not always the case. It can be the case, but it's not always the case. We'll talk about that kind of spring when we talk about artesian wells in the chapter after the next one, or the lesson after the next one. But basically, anytime this groundwater is becoming surface water, right? It's gone to the surface instead of underground. That's called a spring. There are a few different ways that things can be springs on here. There's one that's by a fault, right? Like if this whole thing were shifted upward, there would be a fault that would cause that. In one of the examples on 257, the top right one, there is a layer, the aquiclude layer above an aquifer layer. And so it's kind of like a secondary water table. And then the kind that we'll talk about in the next lesson is when it's limestone, there can be the cave system where all the caves are full of water. And springs can also be hot. That's called a hot spring. And if they're very hot, if the water boils, it's called a geyser. And those are your vocab words. Hot springs and geysers are both vocab words. Do you have questions about any of this? We talked about this quite a bit in the past already when we talked about runoff, infiltration, and evaporation the first time. Do you have questions? All right, bye.